Okay, great. So the next talk's by Youming. He will talk about symbolic determinant identity testing.
Thank you, Shubhangi. I would like to thank the organizers, Shubhangi, Madhu, and Amir, and also all of you for coming. So I'm Youming, and I will talk about this joint work with Gabor Ivanush on an instance of symbolic determinant testing via the so-called star algebra. You will see what star algebra is if you haven't seen it. So that's the plan of the talk. So I will first introduce the problem, the so-called epsilon symmetrization problem for matrix tuples. And I will also explain why we studied this problem, because this problem is actually a very natural continuation of the so-called non-commutative rank problem, which Avi and Katin both talked about yesterday. And then I will give an outline of how to solve this problem and also make some concluding remarks. So what is the problem? But before introducing the problem, I'll just mention a few notations. Most of them you are probably familiar with already. So throughout the talk, the F is of characteristic not two and large enough. The MNF is the linear space of n by matrices you are familiar with, and a matrix space is just a linear subspace of MNF. So throughout the talk, epsilon is just 1 or minus 1, and n by n matrix is epsilon symmetric if the transpose of A equals the epsilon of A. So if epsilon is 1, it's just symmetric. If it's minus 1, it's skew symmetric. So you know them already. And I use S n epsilon F to denote the linear space of n by n epsilon symmetric matrices. And the GLN, you know what this is. And I use MNF M to denote the linear space of M tuples of n by n matrices. Okay, here comes the problem. The problem is that given a tuple of matrices, we define it to be epsilon symmetrizable if there exist C and D, which are invertible matrices, such that every CAID is epsilon symmetric. You just want to make this tuple of matrices, all of them are epsilon symmetric. And it's not hard to cast this problem as an instance of symbolic determinant identity testing because of the follows. So recall that we want to find two matrices, two invertible matrices, C and D, such that every CAID is epsilon symmetric. But actually, if CAID is epsilon symmetric, you just left multiply D inverse transpose and D inverse, and right multiply D inverse. And this also gives you that it's also epsilon symmetric. So it's actually enough to just multiply on one side. So therefore, it's enough to search for one invertible matrix E such that every EAI is epsilon symmetric. Therefore, we can define this matrix space L vec A, which is just all the matrices, no matter whether it's invertible or not, such that EAI equals epsilon AI transpose E transpose. So this is a matrix space, as you can easily see. And then now the epsilon.
What's I there? Is we have for all quantified on I?
For all I, yeah, I forgot for all I. Yeah, sorry about that. So now the problem is reduced just to test whether this L vec A contains a full rank matrix or not. So this is you all know that this is an instance of symbolic determinant identity testing, and we also assume F is large enough. So this means a random efficient algorithm. Therefore, our main result is just basically de-randomize this instance of symbolic determinant identity testing. And so this is our main result, de-randomize this problem. And this is the technique inspired by the so-called star algebra technique, which was pioneered by James Wilson around 2009 when he's a computational group theorist. So he was working with P groups, and he came up with this technique to apply star algebra to algorithms. And also the modular isomorphism techniques by Kistorf, Ivanush, Karpinski, Brooks, Bank, Lux, and Ivanush, Karpinski, and Saxena. So this is about technique. But our original motivation to study this problem was from understanding the so-called singularity witnesses of matrix spaces, which I now introduce. Okay, so this is our motivation. So by the celebrated result of Cabanets and Impagliazzo, we know that actually we don't need to put SDIT in P, actually. If we put it in NP, this already implies that strong arithmetic circuit lower bounds. In other words, this amounts to find small witnesses which are responsible for the singularity of a singular matrix space. And we have seen yesterday one type of singularity witness, which is the subject of non-commutative rank problem. So which is called shrunk subspace. Oddly enough, yesterday actually this is not formally defined, so I just defined here. So a subspace of F to the n is a shrunk subspace or matrix space if the dimension of AU is less than dimension of U, where AU is the span of the union of the images of U under every matrix A in this matrix space. And the non-commutative rank problem basically asks whether given a matrix space, whether there exists a shrunk subspace or not. And as mentioned yesterday, actually matrix tuples with shrunk subspaces are the points in the knock-on of the left-right action by the SLN cross SLN on tuples of matrices. And and also Catton actually conjectured that this problem could be put into P in his GCT5, and now we know that it admits two deterministic polynomial time algorithms by Gargouves, Oliveira, and Wiggerson, and also a joint work of mine with Garber and also K.V. Subramanian. So this is one type of singularity witness. If a matrix space admits a shrunk subspace, of course it's a singular. But unfortunately, there are singular matrix spaces without shrunk subspaces. For example, the simplest one is just a space of 3 by 3 skew symmetric matrices. In other words, put it another way, it said that basically this suggests that the analog of Hall's measure theorem in the matrix space setting does not hold. That is, if you consider all bipartite graphs, by Hall's measure theorem, we know that either it has a perfect matching or it has a so-called Hall obstruction. That is a subset of light vertices whose neighbor is of smaller size than this set. but because of this type of singular matrix spaces, which do not have shrunk subspace, we know all matrix spaces, they can somehow roughly classify into these three types. That is, matrix spaces that does a full rank matrix, and matrix spaces which have a shrunk subspace, and matrix spaces which have neither of these two structures. So SDIT asks us to distinguish between the orange shape and the rest. The non-commutative rank problem asks to distinguish from the blue one from the rest. But these two problems now do not coincide anymore, unlike in the bipartite matching case. So to understand what happens within this red region, namely those singular matrix spaces that do not have shrunk subspaces, is very interesting. But it turns out there are scattered results in the literature about some examples and what happened for example, very small matrices, like Peter mentioned yesterday that we do have a classification for like 3 by 3 matrices and 4 by 4 matrices. But if we go larger than, say, 5, then it's probably not easy anymore. So I think one thing we can do is basically to collect all the singular matrix spaces, interesting incidences, and then examine what is happening there, and then hopefully understand this region more, this red region more, and so that we can get to solve this SDIT problem, putting this SDIT problem in NP. So that's what we do, and here are two classical examples from the literature by Eisenbart and Harris, studied in the 1980s, Eisenbart-Harris from algebraic geometry, Lovas from the combinatorics, and Atkinson from linear algebra. So the first example is those subspaces of the space of odd-size skew symmetric matrices. You know that it's singular, and you can verify easily that it does not have a shrunk subspace. And also the second type may be less familiar. That is the so-called, what I call the skew symmetric induced matrix space. That is how to construct such matrix spaces. You just take n by n skew symmetric matrices, A1 to AN, and then construct such a matrix BI where basically BI, the first column of BI is A1 times EI, the second column is A2 times EI, etc., where EI is the I standard basis vector. And this is a singular matrix space. Why is that? Because if you take any matrix B, which is the linear combination of these BIs, then basically the columns of this B is basically AI times the vector alpha 1 times alpha n. But because these AIs, they are skew symmetric, then you know that this vector alpha 1 to alpha n is in the kernel, left kernel of this matrix. That's why it's a singular matrix space. And basically, Eisenbach and Harris and Atkinson, they proved that under some very mild conditions, they do not have shrunk subspaces either. So these are the two classical examples. There are other examples, but probably these two are the most familiar and most well-studied. But of course, because we are talking about matrix spaces, we know that full rank, whether a matrix contains a full rank matrix or not, and whether a matrix space contains a shrunk subspace or not, they are closed under the left-right action. So then it implies that all these spaces equivalent to them, namely left multiplied by some, say, C and right multiplied by some D, they are also they also do not have full rank matrix, and they also do not have shrunk subspaces. So the question is how to recognize such matrix spaces. And our main result basically gave an algorithm, deterministic algorithm, to decide, to test whether the given matrix space is equivalent to either the first type or the second type. So that's why, yeah, please.
I'm a bit confused. So what's the difference between the brackets in the first bullet and the second bullet?
Okay, so the first is just you have a bunch of, so the first instance is just you take this skew matrix A1 to AN and you take the linear span. Okay, so this is the first instance. The second instance is that you take the BIs, you take these matrices BI such that the first column is the first column of A1. The BI, the first column is the ith column of BI, A1. The second column is the ith column of A2. So another way to look at this is that you take these matrices A1 to AN, you put it at the 3 tensor, and then you rotate the 3 tensor and look at the other slices of the other directions. So that's why they are different, yes.
And the second thing is just the space spanned by B1 through B.
That's right, yes. Okay, any questions? So that's why our main algorithm has something to do with the singularity witness problem. And now I will explain the algorithm for this problem. So recall that our task is that we are given a bunch of a type of matrices, and we want to know whether there exists a full rank matrix in this L epsilon vec A, namely those matrices that satisfy that for every I, D transpose AI equals epsilon AI transpose D. So we just want to find a full rank matrix in this matrix space. Of course, what we will have a linear basis of this L epsilon vec A. And given any matrix D, we want to either conclude that D is of maximal rank or find another D prime of higher rank. If we can do that, then we definitely we're good enough. Here is one very simple rank increasing setting that we will basically use this setting. So if we have two matrices C and D such that the C pulls the kernel of D out of the image of D. If this happens, then some reasonable linear combination of C and D will give you a higher rank than D. So this is easy to say. You just write a linear basis consisting, for example, first some basis vector of kernel of D, and then paired with the basis vector of image of D. Then this is very easy. If you know, for example, one sequences, then it's just the first segment of one sequence. Essentially, what we will do is that if D is not of maximal rank, then any linear basis of L epsilon vec A will contain the matrix that can be used as C. This is a very strong condition, actually. But the caveat is that it's not in the Euro action. It's not in the action of matrices acting on F to the N, but acting on some other linear space. This is the tricky part. So in other words, algorithmically, this is actually quite simple. So we just use the very simple rank increasing setting. But we need to apply it to some other linear space, and the analysis is not that easy. And that's why we need to go to the so-called joint algebra and the star algebra. So firstly, we make some mild technical condition. That is, we assume that the type of matrices. Okay, let's first work with epsilon symmetric matrices. And then we assume that this type of matrices is non-degenerate. That is, the common kernel of these AIs is trivial, and the union of the images of AI span the full space. This is basically you can reduce to this case easily. So we assume this degeneracy condition. And then we define the so-called adjoint algebra of this type of epsilon symmetric matrices. This consists of all the matrices D such that there exists unique C. The existence of uniqueness of this existence is because of the non-degeneracy condition, such that for every I, C transpose AI equals AID. So you can verify easily that it's a subalgebra of the full matrix algebra. And there's a very simple anti-automorphism star of order 2. That is, you just map any D in this adjoint algebra back A to this C. We assume the existence of this C. So this is it's an anti-automorphism because we have the epsilon symmetric condition. And algebras with anti-automorphisms of order 2 are termed as involutive algebras or star algebras, where this star is this anti-automorphism. And one simple instance is just to consider what the transpose does to the full matrix algebra. So this is an example. And now we define a subspace of the adjoint algebra ADJ back A, namely this linear space of star symmetric elements in this adjoint algebra. As the name suggests, that this star symmetric just says that the D star equals D. And this is also a very simple linear this is a linear space. Then you expand the full definition, it just says this. For every I, D transpose AI equals AID. This is simple. You verify that this is also a linear space. It's not a subalgebra anymore. It's a Jordan algebra, but for now, we just use that it's a subspace. And we have introduced all these adjoint algebra and star symmetric elements. So how to connect to the original problem we have? Recall that our main interest is actually this L epsilon A vac A. And for L epsilon vac A, actually, it's defined as this. Then you replace, because if the matrices are epsilon symmetric, then this epsilon AI transpose is just AI. So now that is for epsilon symmetric matrix tuples, L epsilon vac A actually just equals same star A vac A. So this is the connection. So this connects what we want to do, what we are actually interested in with all these new terms we introduced. And here comes the key lemma and the key idea. So suppose let's, for now, just be interested in the epsilon symmetric matrix tuple. And then we are given any matrix D in this any star symmetric element, and we assume that the joint algebra of vac A is L. The key idea is that, as I mentioned before, we do not consider the action of D on the Euro vector space, but on a joint algebra, actually. You consider the action of D on joint algebra, that is, you send any matrix here to just D times E. Because we mentioned that the dimension of a joint algebra of vac A is L, so as a vector space, it's isomorphic to F to the L. And this gives a actual representation of D as basically a matrix of size L by L. And we can also connect for example, the kernel of this D tilde with some more algebraic terms. For example, the kernel of D tilde is the space of right letters of D. And the image of D tilde is just the right ideal generated by D. And we can also verify easily that D is full rank if and only if D tilde is full rank. Now we have the key lemma, which says that if the adjoint algebra is semi-simple, maybe this is the first term that if you do not know about associative algebra, this is the first unfamiliar term. But basically, they said that it's a nice situation. It's a direct sum of simples. If we have time, then I could probably introduce a little bit more. But for now, we put this semi-simple condition on. Then for any non-full rank D in any non-full rank star symmetric D, there exists some C in this. There exists C which is also star symmetric, such that C pulls out the space of annihilators of D out of the image of D, out of the right ideal generated by D. So this is the key lemma, which basically suggests that, putting it in other words, the C tilde pulls out of the kernel of D tilde out of the image of D tilde. And this is exactly where this simple rank increasing lemma will help you. And because you can verify that this is a linear condition, so if you have that, then you have that any linear basis of same star vec A will contain at least one such C. So this is the key idea. Instead of considering this action on the most natural thing, you consider this action on the joint algebra. So, okay, then the algorithm is easy. You just combine the lemma with the simple rank increasing setting. So that is, suppose we have a vec A which is in vec A which is the tuple of epsilon symmetric matrices, and we let C1 to Ck be a linear basis of this same star vec A, and we also fix a large enough subset of field elements. And the algorithm is just that take any non-full rank D, we can just try all the D prime of the form Ci plus lambda JD. So there are not too many of them, polynomially many. And you just choose the one that the dimension of Ci plus lambda JD, when it applied to joint algebra of vec A, the dimension is larger than the dimension when you apply D to the joint algebra of vec A. So but this had this undesirable semi-simple condition. How to remove that? Firstly, if the radical of this joint algebra can be efficiently computed, then the same strategy works. You just compute it and you work modulo the radical. The modulo radical means that you then back it to the semi-simple setting. So this new assumption holds for fields of characteristic 0 and finite fields. Basically, you probably you are good enough with this new assumption then. But actually, I'm cheating. I'm cheating because I'm working with a matrix tuple A, which is already epsilon symmetric. So you see that what's the point of doing all this? The point is that actually the same when you do have another matrix tuple A, which is hidden by some mask E, then the same strategy actually just works. But then you need to handle this mask E because you don't know this E, and how do you handle with that? So suppose this matrix tuple A, which are not epsilon symmetric, but it can be transformed from some epsilon symmetric matrix tuple by some E. Then you take any D from the L epsilon, and you can verify that D equals D prime times E inverse for some D prime, which is in this L epsilon vec B. Vec B consists of all epsilon symmetric matrices. But so we want to compute this D prime joint algebra of vec B. So the red ones are the ones we don't know, actually. It's hidden by some E. So how do you do that? Firstly, you observe that the joint algebra of vec A is actually equal to a joint algebra of vec B because we are projecting to the second component. And you verify easily that This is a joint algebra of vec A, and this is a joint of algebra of vec B. You see that the D, actually they match because when you project to the second component. So this is okay. But we still do not have D prime. How do we handle that? Then we will notice the following. That is, D times epsilon of the matrix tuple consisting of epsilon times A transpose. Here, vec A transpose means that you take transpose for every component here. And it actually equals D prime times L epsilon, vec B. There's something you need to verify, but that's not difficult. And then you see that, but all the blue ones we know, so you apply D times L epsilon, epsilon A vec A transpose, and times then a joint algebra of vec A. You do a little bit transformation, and then you get here. So this means that even with the mask of this invertible E, you can also compute actually D prime times the joint algebra of this hidden vec B. So then you plug in the rest, and you're basically done. Okay, so I've shown you the algorithm where we assume that F is large enough, we can also compute the radical. But actually, without computing the radical, we can also do that, but it requires some non-trivial modification. And even when F is small, we have another algorithm to handle this. So basically, we can cover all the fields. And now the open questions, of course, is what happens for characteristic two fields. And of course, getting back to the singularity weighting is problem. Probably one thing we can do is that we can work with more examples of singular matrix spaces with more shrunk subspaces. There are other examples, quite scattered, I would say. So perhaps pick the one that you like and try to work with it. Hopefully, after gathering enough examples and instances, we will be able to figure out what is happening in the red region. Okay, thank you very much.
Questions?
So where did we use the characteristic is not 2?
Not 2 because of this, when we work with star algebra, we actually divide with 2 in a lot of cases. So especially when we prove this k-lemma.
Right. Now, at some point you had said that somehow, it sounded like the skew symmetric matrices were your big problems.
Right.
Somehow just symmetric you can deal with, and in characteristic 2 you don't have this problem, so...
Oh, sure, yeah, they are of the same thing, but, well, up to a diagonal, but...
Okay, right, I see, okay.
Yeah, so, yeah, characteristic 2, basically, all the star algebra, because you see that it involves the anti-automorphism of order 2, you can imagine that a lot of times you want to divide by 2, too.
Okay, yeah.
Sorry, so I forgot a little bit how to quantify this. So you have this set of matrices, and you are trying to make all of them symmetric or all of them antisymmetric.
That's right, that's right.
And you can also distinguish between those two possibilities.
Yes, yes. Well, you just apply to see whether they are symmetric, or you apply it separately if you want to know which is the case.
And if you ask the question that you are allowed some of them to be symmetric and some of them...
That's also doable, but that's also doable. This involves some generalized condition of the so-called Hermitian condition, but that's also doable.
And that follows from this? Or
this is basically the same algorithm, but you need to because the situation you mentioned, actually, you can also define this joint algebra. It also admits... you can also define a joint algebra, and it also admits an anti-automorphism, the situation you mentioned. Once you fix some of them to be symmetric, some of them to be epsilon skew symmetric, then you can also define all this, so all the strategy works.
Yeah. Any other questions? Thank you, Wayne.